This is the video on horizontally launched projectiles. So for this, we need to understand kinematics, right? So that's the study of those the four conditions of motion: time, position, velocity, and acceleration. So in order to start out learning about the horizontally launched projectiles, we did a lab, and it's called the two-penny drop. So in this lab, there's going to be two pennies, right? One penny is placed just on the edge, so it will fall off the table straight down if anything hits it. So you can see that one is just barely placed on it. Then the other one is launched, not directly into it, but off the table. So it just taps that one that's balancing. The idea behind this is that the penny will fall straight down at the same time that first penny launches, and you should be able to listen if there's a hard floor underneath it for which one will hit first. So that brings us to this question, right? What will hit the ground first? A bullet fired parallel to the ground or one dropped straight down? So not just a penny being slid off the table, but one that's going incredibly fast. So let's take a look at this one. So follow the procedure above and listen to when the pennies hit the ground. So we repeated this experiment. Do the pennies at the same or different times? They should have hit at the same time, right? They're going to hit the ground at the same time. Now, what this means is that they were in the air for the same amount of time. So when an object is launched horizontally, does the horizontal motion affect the vertical motion? No, the horizontal motion did not affect it because they hit the ground at the same time. The gravity pulled them down, and it took the same amount of time for those pennies to land. So when a projectile is being launched horizontally, does the vertical acceleration change? So the acceleration is up and down. And I give you a hint. What is causing the acceleration? It's gravity, right? So the horizontal, or does the vertical acceleration up and down, it doesn't change. Gravity is pulling on both of these pennies the same amount, right? And the ratio of net force to mass is going to be the same. They're going to fall down at the same rate. Now, last one, if you were to repeat this experiment but use quarters instead, would you expect similar or different results? Explain your answer. Same results, right? And it's because we learned in Newton's second law, the ratio of net force to mass, that is the acceleration, and that's going to be the same for all objects. So it doesn't matter whether you use pennies, quarters, nickels, or any mixture of the two, the ratio of net force to mass is going to be the same. Gravity is going to pull them all down at the same rate, regardless of horizontal velocity. So how does horizontal motion affect vertical motion? We kind of already answered this. It doesn't. It doesn't affect the time that that object is in the air. So in order to understand this even further, we looked at a simulation, launching projectiles horizontally. So what we did was we set this simulation to launch from 80 meters up, and we set it to launch horizontally at 10 meters per second. Then we increased the velocity by 10 meters per second. Then we recorded the time that that object was in the air and the x displacement, or how far that object went. So if we look at the graph that we made, when graphing time to land versus horizontal velocity, is the slope of the line horizontal, linear, or exponential? Explain what this means. It's horizontal, right? That blue line, the time that that object was in the air, regardless of initial velocity, was the same. So what that means is that regardless of initial velocity, that object takes the same amount of time to land. So that horizontal motion did not affect the vertical motion. Look at the graph above. When graphing x displacement versus horizontal velocity, did the slope of the, or is the slope of the line horizontal, linear, exponential? Explain what this means. It's going to be linear, right? And what this means is that, well, the faster that initial horizontal velocity is, the farther it's going to land. And it's a linear relationship. So now what we did was we looked at the three conditions of motion graphed against time. So we have position versus time, velocity versus time, and acceleration versus time. So essentially, like, I'll just go over the first few because the first few are the vertical motion, and then we're going to do horizontal motion. You can see it's divided up in these graphs. The vertical motion is blue, the horizontal motion is red. So let's look at the vertical motion. So when graphing an object's vertical position versus time, what does the slope of the line represent? So the slope of position versus time is going to be velocity. And you can see the velocity is not linear, it's exponential. When graphing an object's vertical velocity versus time, what does the line represent? It's going to be acceleration. And you can see that that blue line, it's linear. And when graphing an object's vertical acceleration versus time, what does the slope of the line represent? It's it's a horizontal line, and it's going to represent the change in acceleration over time, or also known as jerk. But then we can look at the red lines, and the red line is the horizontal motion. And you can see that the derivative of them are going to be the same. The slope of position versus time is going to be velocity. The slope of velocity versus time is going to be uh, acceleration, and slope of acceleration versus time is change in acceleration over time. You can see that they look different, right? The position versus time, that's linear. The velocity versus time, that's horizontal. And the acceleration versus time, it's horizontal and it's zero. It's not accelerating in the x direction or in the horizontal direction. So now let's take a look at the conclusion questions, right? So when an object is launched horizontally, how does the horizontal motion affect the vertical motion? Answer is it doesn't. And it's because it took the same amount of time to land regardless of that horizontal velocity. Now, when a projectile is being launched horizontally, does the vertical acceleration change? Why or why not? The vertical acceleration does not change. The up and down acceleration is because gravity is what's causing it. So it's not going to change, right? Regardless of that initial velocity, gravity is going to be pulling it down at the same rate. So let's take a look at what all this means, right? So when we're looking at horizontally launched projectiles, we have the x and the y axis to deal with. So the object will start at the origin, right? Mathematically, it'll work out no matter where you place the origin, but I'm going to place it where it originates. Now we can split the motion of this object into the x and the y components and do those problems separately. Now the x component doesn't affect the y component. So if we take a look at this graphic down here, you'll notice that, well, as it's launching, if we look at the x and the y velocities, the velocity in the x direction doesn't change. The velocity in the y direction does. So if an object is not changing velocity, what can be said about the acceleration? Well, if the velocity is not changing, the acceleration is zero. So yes, it's accelerating in the y direction, right? We can see that it's getting faster and faster. That arrow is getting larger and larger. But in the x direction, so going left to right, that horizontal motion, it remains the same. It's not speeding up or slowing down. So let's take a look at the equations. So these are just the kinematic equations. These are just those kinematic equations. Now, I tell you to don't panic, right? So if an object's velocity is not changing, what can be said about the acceleration? Well, the acceleration would be zero. So what is the acceleration in the x direction? Like we just saw, it's not changing its velocity, so its acceleration will be zero. The acceleration in the x direction is 0 meters per second. So that makes the math a lot easier. So let's take a look at my kinematic equations in the x direction. I plug in 0 for acceleration. Well, what that means is that I only have one velocity. My initial velocity is my final velocity. So I only have one velocity, and what this means, I only have one equation, right? This is the one equation that has time, position, or change in position, and velocity, right? Because we're not looking at acceleration in the x direction because it's not accelerating in the x direction. So we're only adding one equation, and you can see that equation's added down at the bottom. Let's see here. There we go. We only had to add one equation. That's the equation in the x direction, right? And the x velocity and x displacement do not depend anything that is happening in the y-axis at all. If you can do a dropped projectile problem, you can do these problems. So let's take a look at how these connect. What is the only variable in all these equations that does not have a direction? Yeah, the one that doesn't have a direction, the one that doesn't have an arrow above it, or doesn't have an x or a y, is going to be time. Time does not have a direction. And I say yes. Well, technically you move forward in time, but it does not go in the x and the y axis. That's what links the x and the y together. That's just how long this projectile is in the air. So let's take a look how we're going to use these, how these affect it, right? So the origin will be the starting point. The object moves along both the x and the y axis at the same time. Now these problems, we can do a drop projectile and just a horizontal motion with an acceleration of 0, a constant velocity at horizontal motion. So let's take a look at this, right? So the delta t, that's the time interval it takes a projectile to fall to the ground. Delta t does not have a direction. That's just the time interval it's in the air. So the variables on the y-axis, well, it's just a drop projectile. The initial velocity is the vertical velocity. The initial velocity in the y direction will be 0, just like a drop projectile. It's not moving the instant it's fired out of that cannon. Now, in the y direction. Now, the final velocity is the vertical velocity at the end of the time interval. Most of the time, we just say it's when it hits the ground. The object is moving downward in the negative direction, so the final velocity is negative. The acceleration is the vertical acceleration of the object. And regardless of the vertical direction, the acceleration is going to be negative, right? The acceleration in the y direction is negative. It's caused by gravity. It's going to be negative 10 meters per second squared, or negative 9.81. Now, the displacement is how far the projectile drops vertically. It's the final position, which will be the origin, minus the initial position, it's the final position, which would be a negative number, minus the initial position, which will be 0. So I had those mixed up. Delta y, the displacement will be a negative number because the final position is below the initial position. So on the x-axis, well, I've got the vx, right? The velocity in the x direction, the horizontal velocity, it's a constant velocity because the acceleration in the x direction is 0 meters per second squared. Now, the delta x, that's how far the projectile travels horizontally in that time interval. It's the final position, which is going to be positive, minus the initial position, which is the origin. Delta x will be a positive number because the final position is to the right of the initial position. So this is what it means for all of these variables. So the graphs still remain the same, right? So when graphing an object's position versus time, the slope of the line is velocity. When graphing an object's velocity versus time, the slope of the line is acceleration. So if we look at what all this means, right? The acceleration in the y direction, the acceleration in the y direction is negative, right? The initial velocity in the y direction is 0. This is just a drop projectile on those yellow objects traveling. The final velocity, as it's moving down, it's going to be negative. And the displacement is negative because it ends below where it started. It ends below the origin. Now, in the x direction, well, the acceleration is going to be 0. The velocity is going to be positive because it's moving to the right in the positive direction. And the displacement is going to be positive because its final position in the x direction is to the right of that initial position. Now, the last question there is, will the object be in the air longer in the x direction or the y direction? Time doesn't have a direction. The time is what links both the x and the y together because that's just the time interval that this object is in the air, what we're looking at. So we can separate it into the x and the y axis, those graphs. So if we look at the y direction, the y axis, the vertical, up and down, well, this is what my position versus time is going to be because I know that the slope of this line is going to be the velocity. The slope is always changing. The velocity is always changing. It's always going to be accelerating. If I graph the slope of my position versus time at every single point, I'm going to get my velocity versus time. Well, it starts at 0, right? It starts at rest, and it's going to be getting faster and faster in the negative direction. I know that this is a straight line because the slope of this line is going to be the acceleration, and I have a constant acceleration. In fact, I know the acceleration. It's negative 10 meters per second squared. Now let's take a look at the x-axis. So my position versus time, it's going to look like this. Well, it starts at the origin, and I know that it's going to be going to the positive side farther and farther. I know that it's a straight line because the slope of the line is a velocity, and I know the velocity in the x direction is going to be positive, or a constant positive number. So this is my velocity versus time, right? So it's a constant velocity throughout. The instant it's fired in the x direction, it's traveling the same velocity. And the slope of this line is going to be the acceleration. The slope of a horizontal line is 0. So that's what my acceleration will be in the x-axis. So let's do some practice problems, right? Now we're going to be able to answer these questions. Which variable, or these are the questions that you answer, right? Which variable are you being asked to find? What variables do you already know? Which equation has those variables? And you can never go wrong with finding the time. The time is what links the x and the y motions together, the horizontal and the vertical motions together. Now there are 4 problems that we're going to focus on: known height and speed, known height and distance, known time and distance, known distance and speed. So let's just take a look at the first one, known height and speed. An object is launched horizontally from a height of 15 meters with a speed of 5 meters per second. What was the time the object was in the air? With what velocity did the object hit the ground in the y-axis? What was the displacement of the object in the x direction? So let's just ask ourselves, what's the first thing it's asking us to find? The time, right? You can never go wrong with finding the time. So let's see what variables I already know. So let's just look at the y direction only, right? Let's not focus on the x direction. For a horizontally moving projectile, the y direction is just a drop projectile. So I know the initial velocity in the y direction is 0, right? It's not moving up and down like the instant it's fired, right? The displacement, this one's tricky. Height is a scalar quantity. The displacement in the y direction, it's going below where it's going to end below where it started, so it's going to be negative. So my displacement is going to be negative 15 meters, and I do know the velocity in the x direction, it's 5 meters per second. So let's just look at the y coordinate, right? Let's find the equation that has all 4 of these variables, or let's find the one that doesn't have the final velocity in the y direction. So if I look at well, I just plug everything that I know into that second equation, and I'm going to get the time is 1.73 seconds. Now notice my time interval, yeah, I put it 2 different places. I put it in the x coordinate and I put it in the y coordinate. They're the same time. That's just the time that it's in the air. The time does not have a direction. So that's just the time it's in the air. Now I can solve for the final velocity in the y direction. This is just finishing up a drop projectile problem. This can come into play if you wanted to find like the velocity at which it hits the ground. All right, so let's just take a look at that. I can use any of the equations. The bottom one would be best, just because if I got the time wrong, I still would not get the velocity wrong. But I'm going to use the top one. It's easier because I'm confident in my answer. And you can see I have the final velocity in the y direction. Now let's solve for how far did it travel, the displacement in the x direction. So I just plug it in my one equation that has the x variable. So I just multiply the velocity in the x direction times the time, and I get how far it went, 8.65 meters. All right, now let's do the known height and distance. So an object is launched horizontally from a height of 20 meters and lands a distance 16 meters away. What was the time the object was in the air? With what velocity did the object hit the ground in the y-axis? What was the velocity of the object in the x direction? So let's take a look at the time. You can't go wrong finding the time. That's the thing that links the x and the y together. So I know, same thing. The first part is just a drop projectile. Now be careful because the displacement is going to be negative. It falls from a height of 20 meters. Remember, it's going down 20 meters below where it started. The displacement is going to be negative. The initial velocity in the y direction is going to be 0 because it's just a drop projectile. I look for the equation that has all of these, all 4 of these variables, or the one that doesn't have final velocity, and I'm going to get that second one. Plug everything in, solve for the time, 2 seconds. Well, now I can solve for the final velocity again, right? So all 3 of those will work. I should use the bottom one. I use the top one because I'm confident in my answer, and I can solve for the final velocity in the y direction. Last thing, I can solve how fast it was traveling to go that far. So I can solve the velocity in the x direction. I use my one equation with the x direction, and I just take 16 divided by 2, and you can see that it might be cut off a little bit. It's 8 meters per second. So this is a known time and distance. An object is launched horizontally and lands a distance of 42 meters away 3 seconds later. What was the displacement of the object in the y direction? So how far did it travel down? With what velocity did the object hit the ground of the y-axis, and what was the velocity of the object in the x direction? So first thing it's asking me to find is the displacement in the y direction. I know the initial velocity in the y direction is 0. It's just a drop projectile problem, right? And the acceleration for all these in the y direction, negative 10 meters per second squared. I know that it fell for 3 seconds. So I'm looking for the equation, once again, that has everything that in the y direction, that is everything but the final velocity. It's that second one again. So it fell down 45 meters, so negative 45 meters. That's the displacement. I can solve for the velocity. I'm going to use that top equation, negative 30 meters per second. Last thing I can do is I'm going to solve, well, what velocity? How fast was it going when it traveled? So I just plug everything into that equation, just 42 divided by 3. All right, so known distance and speed. So last one that we're going to go over today. An object is launched horizontally with a speed of 25 meters per second and lands a distance of 68 meters away. What was the time the object was in the air? What was the displacement of the object in the y direction? With what velocity did the object hit the ground in the y-axis? So first thing I'm going to do, you cannot go wrong with trying to find the time. So this one we're going like the reverse direction, basically. We do have to start with the x direction first because we know how far it went and we know how fast it went. So I can solve the time interval. Now I can work backwards to find the displacement. So I'm going to find out the height that it landed by using the one equation that has those four variables, or the one that doesn't have final velocity, negative 37 meters. So that's how far it fell from. Then I can solve for that final velocity in the y direction. But that really only comes into play if you want to find like the absolute final velocity that it lands with. All right, so now let's look at some conceptual things. The question is, what is orbit, right? So International Space Station, it's 254 miles tall. If you were on the top floor, the acceleration down would be negative 8.66 meters per second squared instead of the negative 10 or negative 9.8. It's about 90% of what it was. So the biggest misconception people have is that once you just get to a certain point in space, boom, gravity shuts off. Well, that's not true, right? If you look at astronauts in the International Space Station, it does appear as if there's no gravity, right? You can see them floating around. Orbit is simply a projectile being launched horizontally, right? Now, however, it is moving so fast at about 17,500 meters per second, and the x displacement is so large that the Earth curves out from beneath it. And the direction of the acceleration is always changing because it points to the center of the Earth. So basically, anything that's been in orbit, like that International Space Station, has been falling for over 20 years and still hasn't hit the ground. So what does this mean? Well, just like a drop projectile, well, I have acceleration, but the velocity is moving horizontally, right? So it's moving incredibly fast. So it's just a horizontally launched projectile problem. But notice where it's going to land. There's nothing there, right? There's nothing where it's going to land because it's going to launch so far away, the Earth curves out from beneath it. Now, the acceleration is going to be pointing towards the Earth, and the velocity, well, it still has a horizontal velocity. So you can see at every single point, it's just a horizontally launched projectile, but it's moving so fast, it's falling over the curvature of the Earth. So yes, if you were that tall, if you were that high up, 254 miles in a building, yeah, you would feel pretty much normal. That might feel a little bit lighter. Something falls off a desk or something, you would notice it falls a little bit slower, but you would see that International Space Station zip by every 90 minutes because it's just horizontally moving over the curvature of the Earth. So orbit is when a projectile is moving at orbital velocity. The projectile will fall towards Earth with a trajectory which matches the curvature of the Earth. So Newton hypothesized orbit by thinking about a cannon on a hill and firing it. The faster the cannon ball moved, the farther it would travel. He thought there could be a speed at which a cannonball would fall over the curvature of the Earth and come back and hit him in the back of the head. So you can see that in that graphic here. Right, the orbital velocity of Earth is about 5 miles per second. So you can see I provided a simulation there, and there's a website that shows like the ISS. You can see it in the night sky. It just shows like it's a pretty bright star. It looks like a bright star just moving across the sky. And here's just an interesting one. Have you ever wondered how many people are in space right now? If you go to howmanypeopleareinspaceriightnow.com, it just shows you the number and a link to all the people that are in space. So just a couple interesting things there. All right, so last thing we're going to do with horizontally launched projectiles, collect some data and do some problems with the horizontally launched projectile lab. So at each table, there's going to be a marble, a meter stick, and a blue ramp with numbered notches on them. The marble will be rolled down the ramp. It says 3 times. We're just going to do it once from each notch. The displacement of the marble traveled from the table will be recorded. From these measurements, the initial horizontal velocity, the instant the marble left the table, can be calculated. So you can see here, there's a ramp with different notches on it. They're pretty much evenly spaced. It's far enough back from the edge of the table that it rolls. The marble is going to bounce. It should even out, and then it's going to launch. And you can see that picture on the left here. We're going to be measuring how far that marble is launched off the table. So the first thing you need to do is record the height of the table in centimeters using the meter stick. Convert that measurement to meters, then use the kinematic equations to calculate how long it would take an object to fall from that height. Then just roll the marble down the listed notches on the blue ramp and calculate the time the marble would be in the air, horizontal velocity when it left the table. Make sure the horizontal displacement is recorded in meters. So we need our answers recorded in meters. So record the height of the table in centimeters, use the meter stick, convert that measurement into meters, then use the kinematic equations to calculate how long it would take. So you can see here, the height of the table that we're using is about 92 centimeters, right? We're just going to use 92. So this is just a drop projectile problem. Hey, an object falls, drop projectile. A marble falls from a table that has a height of 0.92. We have to convert it to meters. What is the time interval for this fall? So I'm looking for the time interval. So I know the displacement and I know the initial velocity if I dropped it straight down. The initial velocity is 0, and this is the biggest mistake people make. The displacement is going to be negative, right? So I just said height. Height is a scalar quantity, does not have a direction, but displacement does. Because it ends up below where it started, the displacement is going to be negative 0.92 meters. So I just look for the equation that has these 4 variables, the one that doesn't have the final velocity, and I can solve, right? It's for the time interval, 0.4290 seconds. So now we rolled the marble down from those notches, and then we're going to calculate, the time it was in the air. Now we know that the horizontal motion does not affect the time that it's in the air. So it's going to be the same. That time is going to be the same no matter what the horizontal velocity be. It could be dropped straight down, or it could have been fired like as fast as a bullet. It's still going to take 0.4290 seconds to hit the ground. Using that, when we roll it off the notches, we'll be able to calculate how fast it was rolling from the table. So the first one, I'm just going to do notch 1, 0.1700 meters. That's how far it landed, or 17 centimeters. But I need them in meters when I'm doing the math. So let's calculate how fast it was traveling off that table. A marble is rolled off the table horizontally from a height of 0.9200 meters and lands a distance of 0.1700 meters away. What was the time the marble was in the air? With what velocity did the marble hit the ground on the y-axis? And what was the velocity of the marble in the x direction? So we're solving the time. It was in the air. We already did this. This was just the drop projectile problem. And you see, I meant to put for the displacement, it should be negative 0.9200. I did put it in the equation correctly. But the time interval, yes, 0.4290 seconds. Now I'm going to solve the final velocity. Not really concerned with this one in the y direction. I'm just looking for that velocity in that x direction. So you can see that I'm just going to plug it into my equation. All I do is I take that 0.17 meters divided by the time that it was in the air, and that will get me, I think that's 0.363 meters per second. And I'm just going to do that for all the notches now that I know how far that marble traveled off the table. So when we graph it, when an object is launched horizontally, well, we know that the horizontal motion does not affect the time it takes that object to hit the ground. How is this applied to the lab? We just calculated how far or how long it would take an object to fall from the table, and we just used that as the time for every one of these problems because the horizontal motion does not affect the vertical motion. Look at the graph above. When graphing the horizontal velocity versus notch on the ramp, is the slope of the line horizontal, linear, or exponential? So you can see that it's a linear, right? It's about linear. I did put the r-squared value, so you can see it's pretty close to 1. So they're pretty close to that trend line. If the marble was dropped from a 6th notch, how could the horizontal velocity be found from the graph? There's an equation up there, right? On the x-axis, the notch on the ramp. So if I plug in 1, I should get close to how fast it was moving with notch 1. Well, because it's going to extend out indefinitely on this line, if I just plug 6 in for x, I'm going to get about how fast it would be traveling if there was a hypothetical sixth notch. Now, when the marble was launched horizontally off the table from a different notches, does the vertical acceleration change? Why or why not? Nope. Vertical acceleration doesn't change because what's pulling it down from the ground is gravity. And the gravity is going to be the same for all of these problems. So it's going to take the same amount of time for all of these projectiles to land. So, as always, there's just too much unknown in the universe to take a break from learning. Get out there and question everything.